Let's move to the next talk. It will be by Alexander Vikman, who will talk about mimetic mix, whatever it means.
So, sorry, I have no idea what is the overlap with respect to my previous talk, I mean, in the audience. So therefore, for those of you who have seen part of these equations yesterday, I would like to apologize. But it's really a pleasure to give a talk at Quarks, even at virtual Quarks. And 2 talks is better than 1. So thanks a lot for organizing this workshop. So thanks a lot to Zhenya and to Valery Anatolyevich. Fantastic workshop. Okay, so just in order not, so that you don't really forget what was it about, and you know, maybe you will be bored and so on, I will tell you straight ahead probably what's the message. So the message is, you can see it by this formula, but in text, one can say the following, that if you do a simplest modification of gravity, what in Schindler's terms would be type 1a, as far as I remember. And actually you introduce this kind of conformal substitution, or if you want, you try to write some simplest version of host, but putting the conformal transformation everywhere, including matter, then you can actually mix what was this mimetic dark matter and mimetic dark energy. And surprisingly, you will obtain our old beloved K essence. However, the only difference will be that in front of the Lagrangian of this K essence, there will be a constant, but this constant is constant of integration. So basically, it depends on your initial data. And for me, it was surprising. It's I don't know how to properly digest it. So formally speaking, you can think about it as a very complicated Weyl-invariance theory, which at the end reduces to this stuff. Or you can think that that's basically the simplest result of it. So there are probably different constructions how one can obtain it. So why it is interesting? Because, well, first of all, you found some new representation for this K essence. And secondly, the point is that this correspondence may be not unique. So in some cases, you could find kind of meta theory, which covers actually different K essences for different ranges and so on. And moreover, basically, this Q is the equation of your initial data. It's also subject to quantum fluctuations, as I told you yesterday. So it's another global dynamical degree of freedom, like lambda in unimodular gravity, and so on. And basically, it's kind of funny that imagine this K essence is dark energy, or maybe dark matter, like Gauss condensate. In that case, the scale of dark energy or dark matter is directly given through, let's say, quantum cosmology, okay? Or some initial process which fixes this energy scale. Okay, so now basically this work is, so I will review old stuff just to introduce you what is this mimetic and blah, blah, blah. Let's see, if you want, it's the simplest DOST, or DOST for poor people, if you want. And I will, but you know, it's a good DOST because it's very symmetric. And the new material in this presentation is actually based on our ongoing collaboration, and there will be a paper published very, very, very soon. And this collaboration with my student Pavel Jerushek and Masahide Yamaguchi from Tokyo Institute of Technology and his PhD student Keige Shimada. Okay, so let me, maybe I will try not to bore you too much, but I kind of review what is what. So simplest fluid like dark matter is, if you want, simplest action for a field theory. So it has a Lagrange multiplier rho, and it has a scalar field phi. So these are both scalar fields. And this thing reproduces dust, okay, just normal irrotational dust. Because if you look at the menu, that's how it looks like. So you can write for velocity, and then the funny properties of this action are the following, which I'm kind of going to exploit, is that it's scale invariant, so there is no additional mass parameter, okay? So there is no fixed scale. So then it has global symmetry, namely shifts with respect to shifts of this velocity potential. It's kind of fake, but less fake violation of Lorentz symmetry than in this untitled Bohm construction, which I'm going to mention too and compare. It's fake in the sense that if you fix rho to be 0, then nothing changes. And if you don't couple to it, it's just the presence of some dust in the universe, you would not care much. So, but of course, if you introduce couplings, then the things can change a lot. So dark matter here is represented through this Lagrange multiplier rho, and that's your dark matter energy density. Okay, so now why I was reviewing these properties, because actually it's kind of related to Ostrogradsky construction, because I'm going to basically promote this theory to high derivative one, and I want to stress the similarity with the Ostrogradsky construction. So namely, if we look at the canonical momentum of the system, then for example, if we go to its own preferred reference frame, then the system is linear in phi dot. Okay, then immediately you can say what is the canonical momentum in this frame. So namely, it is proportional to your energy density. And I presume we will hear a lot about Ostrogradsky problems and so on. So here, importantly, this canonical momentum cannot change sign, right? Because for that, you would need to change the sign of energy density. So basically, in order to exploit the unboundness of Ostrogradsky Hamiltonian, which is here just basically proportional to the same pi, you would need to cross through the region where rho is equal to 0. However, it's impossible because the equation of motion is just rho dot is equal theta rho. And if rho is 0, that's your fixed point. So basically, there is a kind of, there are systems where you have kind of similar to Ostrogradsky structure, which can originate actually because of that from high derivatives. But nevertheless, there's no problem with Gauss at all, because, well, you need to change your energy density to be negative, and classically, it's impossible to do. By the way, quantum mechanically, it's also not a good idea to change it because this rho is in front of d phi squared, so that's not a good idea. Okay, so then this hint, this Ostrogradsky hint, linearity in canonical momentum, kind of and scale invariance on top, can give us a thought that maybe there is some Weyl-invariance behind it. So Weyl-invariance is more general than scale invariance, and it corresponds to changes of the metric with arbitrary space-time dependent function. And that's I have already said you. And so basically this would represent the same dust in a highly symmetric fashion. Okay, so and that was actually done, but with different motivation in what was called mimetic gravity or mimetic dark matter in the paper by Ali Shamsuddin and Slava Mukhanov in 2013. Sorry for getting you bored because I'm reviewing this old stuff. So the point is that basically in front of some auxiliary metric, you can write a conformal factor and use this composite object everywhere in your normal action. Okay, so then basically this G mu is a physical metric of free fall. The G mu tilde there is auxiliary metric, but in your action it's exactly this auxiliary metric which is going to be a dynamical variable. Okay, so basically everywhere you plug in this, and then it has funny properties. So first of all, it becomes then manifestly Weyl-invariant with respect to transformations of this dynamical variable of G tilde, and B, it gives you immediately built-in constraint. So the presence of these constraints is a very important issue, so this will reappear many times in this talk. Okay, so then basically what you can do, you can just plug it in, then you want to maybe reduce the order of your system by writing, like similar to Ostrogradsky, you plug it in and then you write Lagrange multiplier saying that this field X is just a kinetic term. And then you abuse Weyl-invariance, go back to gauge invariant variables, and then tralala, you got dust, okay? So that's the simplest procedure. So then there is no Weyl-invariance at all, but formally speaking, the original high derivative system would be was what you needed. So that was also realized in slightly different fashion by Alexei Golovnev, and then later it was also discussed by Andrei Barvinsky. Okay, so funnily enough, it turned out that actually this machinery of writing some conformal degrees of freedom or some conformal fields is an old story. So in particular, you can just canonically normalize this X, or almost canonically, because it's a ghost in my signature convention. So you see it's wrong, it has a wrong sign, but otherwise it looks almost like a normal scalar field theory, right? Suddenly. So if you want that, it's kind of surprising that this action corresponds to dust. And Andrei Lind and Renata Kalash in 2013 actually called such fields, such fake degrees of freedom, conformals. Okay, so now let me take the similar picture for dark energy. So basically, that's not a Bohm action. You see, it has a kind of very similar structure. So namely, it has scale invariance, so there is no fixed scale in the action. Well, on top of that, there is not just shift symmetry with respect to constant, but shift symmetry of this vector with respect to divergentless vector. It has also this violation of Lorentz symmetry. However, here it's even more fake than before. And similarly to dark matter, lambda here is the Lagrange multiplier, and that's your actually energy density for the cosmological constant, as you can easily verify by taking the menu. Again, similar to Ostrogradsky Hamiltonians, the system is linear in canonical momentum. And funnily enough, you cannot exploit this property because this momentum is always conserved. So therefore, you pick initial data. Yes, your energy density can be as low as you want, but after that, it doesn't allow to be changed. Okay, then basically what we have done with my student, we just tried to really do the same what Shamsuddin and Mukhanov have done for dark matter. And the funny thing is, so we found substitution. So now instead of G mu tilde, we write H mu, because it's actually a different object, right? It's a different auxiliary metric. And what is surprising, so basically you can write this auxiliary metric, you can write a conformal factor as for divergent, sorry. And this vector field has conformal weight 4. Just to remind you, conformal weight 4 means that it scales on the Weyl transformations as omega minus 4 if you change the metric as omega squared. It also has this gauge degeneracy, and then trulala, because we are in gravity modification section. So that's the horrible action, which one would say has higher derivatives and all problems, but in reality it's just stupidly written normal and Untitled Bohm. Or if you want, you can immediately see that that's just equivalent to unimodular gravity. Okay, these equations are just there because in some of my talks people were asking whether the equations match or not. Okay, so actually more familiar action, again, we can introduce a conform one, write it blah, 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 and then exploit Weyl-invariance, and then through la we got an Untitled Bohm in this way. That's all classical because you see I used Lagrange multiplier construction, so I don't know whether really quantum properties would be the same or not. That's an interesting question, but okay. So then instead of this V mu, one can use normal connection because this V mu is some strange vector field, conformal weight 4. It's not typical because usually people use connections, A mu, and conformal weight of connection is just 0, so it doesn't change on the conformal transformations. And then with my students, we have done, well, we realized how to do it in a different fashion. And basically through FF dual, through what is called Pendragon invariant. And you see, it turns out that this FF dual automatically gives you what you want. Of course, we first tried this FF, but it turned out that Shinji has done it already. So therefore, you need to have FF dual. So and what's the deal? The point is that this FF dual is just a divergence of Chern-Simons current. This Chern-Simons current is some complicated object, but importantly, it has conformal weight 4. And on top of that, the gauge transformations introduce the same shift as we wanted for Untitled. And most importantly, this substitution is a legitimate one because the only thing what was important in the Untitled is the time component of the vector W. But here in this time component, we substitute something what doesn't have time derivatives, because CT doesn't have derivatives of A. So therefore, it doesn't change the structure. Well, one can check it explicitly. Again, here we're in a modification gravity section. So this looks like horrible gravity modification. In reality, it's just simple unimodular gravity. Basically, the same GR augmented with an integration constant, which is your lambda. Okay. Just the same story with the conformon. I just go very quickly through. And now I'm coming to main subject of basically how to extend it. Okay, so now it seems that on cosmological scales, if you don't care about caustics, if you don't care about really complicated physics stuff, you could be satisfied with this action for whole dark sector, for both dark energy and dark matter. And then the equation would be the following. So of course you can write here the substitution which I mentioned. Let's denote this as X and this is as D for simplicity. And then you see the equation is the following. If we use it, both of these components of dark sector could be obtained from this Weyl, so to say, symmetrization or fake symmetrization. So can we obtain the whole thing in the same way? So basically, can we write kind of new mimetic substitution by mixing both these operators X and D? So here, the subscript H actually means that we use the same auxiliary metric H mu to define X and D. So later, it turned out that it's a bit easier to write D not as for divergence for some purposes, but this F of dual. But you can think it's basically either or. It doesn't matter. Okay. Starting from that, I can tell you that we have some answer for that, but that goes beyond of what I wanted to say, it turned out to be. And the point is that just by writing this mimetic mixing, so this conformal factor, which is a function of both operators, you do not create the sum. So you create something new. So basically you entangle dark matter and dark energy and you get something new. I told you what it is. It's actually k-essence. Now let's see why it is the case. So in this mimetic construction, what was important is that this metric for geodesics is actually invariant with respect to all transformations of the dynamical variable metric. So now this X has conformal weight 2, D has conformal weight 4, and then it implies that omega, this conformal factor, should be actually a homogeneous function of variables X and square root of D with degree of homogeneity 1. In that case, it would have conformal weight 2, and that's exactly what we need. Okay, so now what are the examples of such substitutions which one can entertain? Yeah, for example, you can sum them, take a square root, do things like that. As you see, it can be very complicated in reality. Okay, so now if we really do the same game as I already have done twice, or maybe even 3 times, employing these conformons, then by getting rid of high derivatives, I would get this constraint, okay? And now what is important? So formally speaking, I could start from this guy, which is not Weyl-invariant, right? The substitution, which would not be Weyl-invariant. In that case, there would remain dependence on chi, and I would not be able to find this new, or if you want old, J mu and rho, so that this dependence on conformon disappears. But if this omega is a homogeneous function of degree 1, then I can do it. So now you see I reduce the substitution to just a theory with a constraint. Okay. Still, it does not look like quiescence if you look at it. But then the point is the following, that this constraint allows us to use implicit function, and this implicit function would give us, for example, because we want to map it into quiescence, that the Pentragon density or Pentragon invariant, better to say here, is just some function of x and phi. So basically, that of course only happens if the derivative of omega with respect to d is not vanishing, because otherwise, well, we would not be able to solve it. But if we can, then we can find this function. So here, interestingly, actually, one conformal factor could encode many of such functions f, right? There may be non-uniqueness and so on. That's pretty interesting to understand what would it actually mean. Okay, now let's look at energy momentum tensor of this stuff. And what we see that it has already a form of a perfect fluid provided the mu phi is time-length. So now, however, let's look at the equation of motion for, let's say, gauge field. Suppose we use here gauge field. In that case, what we see immediately is that if f of dual is not equal to 0, then you could immediately obtain that this rho omega d is equal to a constant. So very good. Now we know that we can substitute this constant back into this term, right? So what we obtain clearly has now a form of quiescence, because this d in conformal factor omega has been already expressed through phi and x. Okay, so basically now we can even infer that funnily enough, this Pentragon invariant is just proportional to the Lagrangian of your resulting quiescence, which is, well, kind of unusual, I would say. And here, of course, we actually, for this setup, we don't even need anymore that the mu phi is time-like or not. What is formally kind of needed, that this d is positive, but in reality, we could write the square like modulus and nothing would really change substantially. Even though clearly there is no quiescence when d is equal to 0. So therefore, that's kind of interesting coincidence. And then structurally, this is very, very similar to what we were doing with Andrei Barvinsky and Andrei's student Nikita Kolganov, both organizers of this conference. But it seems that this generalized unimodular gravity suggested before by Andrei and Sasha Kamenchik, that is actually richer. So basically, it kind of reduces to that in some cases, but there is no general mapping for all solutions to this construction. Okay, finally, let me give you one particular example, very simple one. So suppose we take just a superposition of them. So basically, we take a sum of these factors. I can even write in front of d a function of phi, because this function is phi, it has conformal weight 0, so therefore I could write it whatever I want. And then if I plug it in everywhere, what I will obtain actually Gauss condensate. You can think that this alpha is constant if you want. So this is pretty funny, because if you want, so we found in this way a Weyl-invariant formulation for arbitrary quiescence, maybe even for many of them simultaneously, right? And then the scale in front of this each of these quiescences would be some global degree of freedom fixed by some initial data. Okay, I think, Zhenya, how much time do I have? I think I'm exactly on time.
You still have 5 minutes.
Okay, I think that's okay. Let's leave it for questions. So thanks a lot for attention.
Okay, Alex, thank you very much. So please ask questions. Let me ask a question. So it's just naively. So this type of construction, imagine, I mean, if you go back and show your slide with the quiescence, energy momentum, yeah. So what is practically, why is it better to use this construction instead of just putting in the Lagrange and the, I mean, the quiescence, you know, K of X? What's the advantage to use this picture, you know?
For late universe, nothing, because I mean, this Q is your constant and that's it. And then after that, it's this quiescence. Though I don't know what's about quantization, because you see, we used a lot of this. Basically, this is only on classical solutions, because as you see, I used equations of motion. So this equivalence is only on shell. So would be, of course, very nice if through this highly nonlinear construction, we could solve issues with maybe some nonlinearities, I don't know, caustics or things like that, but I don't know. But basically, it's an extension. What may happen is that when this quiescence is singular, it can be glued to another quiescence on singularities. So that gives you more richer dynamics. But that's what we kind of also investigating and trying to understand what happens there.
Sorry, how do you mean if it's singular, you can glue it with your construction, you can glue it? Or?
No. You see what I mean? Let me show you something. What I mean is the following. Let's look at this constraint. Now imagine you have some singularity. So singularity would mean that this, let's say, pressure is infinite or something, okay? That something happens there, right? Mm-hmm. Or let's say phi is not well defined. Then you may not be able to find a single function d as a function of x and phi. There could appear some branching, or I don't know. Potentially, we don't know yet. We are trying to kind of understand what exactly happens for such, if you want, pathological singular points. But potentially, you could have with one meta theory, many through implicit function theorem, you know, it could have branches and God knows what. So you may have different quiescences. Maybe you can glue them together on some singularities, for example. Mm-hmm. So that's one thing. And second thing, you know, usually you kind of, well, first of all, you kind of embedded it in a more symmetric setup, similar to what we were doing before for dark matter and dark energy. And lastly, in some cases, you know, you would write this quiescence, but you would not know the origin of the energy scale in front of the whole Lagrange. Mm-hmm. But here, you're just not even allowed to. Basically, you can only ask what is it in the very early universe when the whole thing will fluctuate strongly. So basically, because this Q is a constant, but in reality, it's a dynamical variable. Mm-hmm. But it's a global one again. So therefore, you would need to know what fixes its value.
Actually, can I ask you if you can go in the very beginning where you introduce the dust in terms of rho and phi? Yeah, this type of thing. Okay? Yeah, this is fine. If I forget about lambda, for example. So yes. So this when you are doing this rho phi construction, rho is fixed also by initial data or what?
Oh, look, rho phi is very easy because that's dust, and for dust we know what initial conditions do we need. We need initial energy density as function of space in Cauchy hypersurface, and we need the 3 velocity as function of Cauchy hypersurface. In this case, 3 velocity is easier because it's not even a vector; it's a potential flow. So therefore, we would need phi as a function of an initial hypersurface. And then basically knowing rho of x and phi of x, we can evolve the system forwards in time.
No, I was asking a simple thing. This rho here is also like a global variable? Is it?
No,
like,
no. Look, it's a
no.
local variable in a sense that it's a field. So that it depends. So basically, it depends on initial conditions on X. So if you want, you take Cauchy hypersurface, and this rho is a field. So therefore, it's a function of your position initially.
And
like normal dust.
It evolves with time also.
Yeah. But it evolves trivially. Basically, you kind of shift it in some way, right? But this Q is just stays. It's a global constant. So it is space-time and it's space independent, and the whole dynamics is global. So it only cares about the whole Cauchy hypersurface.
Okay, thank you.
Which also makes it interesting what to do with, like, in the presence of horizons or things like that. I don't know.
So we have other questions. Valery Rubakov and then Andrei Barvinsky.
Yes, I have a question concerning your equation that your D is a function of X and phi, right?
Okay, just a sec.
Right.
Yes.
Yes, here. And you just don't care, but D is actually not a elementary field, right? Elementary object. It's rather like FF dual. And the FF dual is not just arbitrary thing, right? In, say, electrodynamics, it's a divergence, total divergence of something. So is the fact that D is a very special object, does it play any role here, or you can think of it as an elementary object and not care about its sort of internal structure?
Very good point. Honestly speaking, we kind of should care about internal structure, but at the end, in this construction, we kind of don't, because you see, so formally speaking, in this formula, this omega is still a function of X and D. And then basically we just solve from this constraint equation, this D, and then plug it in. So I think in order to kind of, we don't resolve this solution,
right? If D is FF dual, then you might not have a solution to this in terms of the gauge potential.
Oh yeah, that's a good point. Of course, it is potentially possible that there is none, but bear in mind that there is one interesting property. So here we don't include normal kinetic term for this gauge potential. So in some sense,
simply that not every function can be understood as a total divergence of something, right?
Oh yeah. No, of course. That's definitely true. That could provide additional kind of constraints on phase space of this x and phi. That's true. That's true. On the other hand, you see,
or you may be interested in solving in terms of phi, given that D is sort of has to obey some conditions.
Right. In reality, you see, we could do an opposite. Actually, we could do the opposite thing. If you want, we could, in this formula, write X as a function of, forget about phi. Suppose it's shift symmetric. Actually, that's what we wanted from the very beginning. This phi is just makes things a bit more complicating. But the interesting thing is we could solve with respect to X, of course. That we could also do. And then X would be a function of this FF dual. And so in this case, this whole term nu will be kind of functions of this FF dual. And that's, if you want, in addition, and a different representation of the same K-essence, which is very weird. But you see, otherwise it's a kind of strange thing, because in reality what we need to solve, it's kind of nabla mu c mu is equal to this whatever function, and then formally speaking, because it's just a divergence, I can probably solve this equation, I would say. Then I find the Chern-Simons basically vector, or whatever current is sometimes called, And after that, I would need to find, for the Chern-Simons current, I would need to find the corresponding H potential. That's a bit harder. So you see, on this more detailed level, that would be very interesting to understand. So maybe there is some topological properties which could limit it, but so far we have not basically found any constraints. So we thought about it a bit, but not that we found any limitation.
Okay.
Okay.
Thanks. That's a very good question.
Andrei. Andrei Barvinsky, we cannot hear or see you. Please. Yeah.
Sorry. I just wanted to ask a question which goes somewhat beyond your goal, Sasha, to generate global degree of freedom. What I mean is that, well, when you model the behavior of the perfect fluid in terms of the scalar field, you actually exclude rotational behavior, which might be somewhat restrictive for generic situation. So what would be if you would replace F times F dual in your method of mimetic, so to say, conformization of the theory? If you would just take F times F structure, so that the vector field will be kind of a real degree of freedom, and it might actually play the role of a velocity potential for a generic description of a generic perfect fluid.
Very good point. Of course, this setup allows for a lot of generalizations. You see, we were also thinking maybe to take instead of X. So you see, you can do mimetic mix not only for X, but for the scalar field, but just for this F squared. But that would be much more involved because it's less trivial, because you see, I can tell you what the key property is. The key property is this equation. So through this equation, when F dual is not zero, we know that this Lagrange multiplier and omega are related to a constant, like this. If you add the explicit dependence on, let's say, another invariant on F squared, or trace F squared, because here, basically, we wrote it for whatever, for abelian one, but you can use non-abelian one. In that case, this property will be lost. It will be another complicated equation. I don't know what it is, but you know, structurally, the dependence on F of dual and on F squared is a very different thing, because, for example, what Shinji investigated was this mimetic substitution with F squared.
In particular, you would not be able to pull F through the derivative as you can do it with F dual, yeah? Exactly.
But you see, with what Shinji was doing, they obtained a kind of, also, if you want, a substance which models special curvature. So basically, if with F of dual you model lambda, with just F you model special curvature, so it's much more complicated object. So here, of course, one could write immediately, you know, either mixing F of dual with F squared, or mixing, let's say, F squared with X. That's also possible. It would give you different series.
Say it again. Who did this?
Shinji Mukayama.
Shinji?
Mukayama-san, yeah.
Okay, maybe you would send me the reference to this.
Absolutely, yes.
Mukayama-san paper. Okay, thank you very much.
Thank you too.
Okay, thank you very much. So thank you, Alex, again.